Alright, in this video we're going to look at examples of proof by mathematical induction. If you haven't watched our previous video, you might want to do that before you go on with this video, because in the previous video we laid the foundations for mathematical induction and explained the basic steps of how this method works. So in this video we're just going to show how those methods, those steps work out in practice. Alright, so in A we have the proposition is that n into n squared plus 2 is always divisible by 3. Alright, so step 1, which is the base case, we are going to let n be equal to, say, 2. Okay, then if we substitute 2 here, it's going to be 2 into 2 squared plus 2. It's going to be 2 times 6. This is going to be 12, which is divisible by 3. So we conclude that the proposition is true. Notice that in the method of proof by induction, you want to use a lot of words to explain your steps and to explain your reasoning and everything. We just write out formulas without explaining. Then you are going to find that you collect the minimum in terms of credit. So in step number 2, which we said is the hypothesis step, we assume that the formula or proposition in this case is true for n equals to k. In this case, what it does mean is that we assume that p of k, which is k into k squared plus 2, we assume that this is divisible by 3. So assume this is divisible by 3. Now, earlier we mentioned that something being divisible by 3 implies that that number is a multiple of 3. So actually this assumption is saying, to put it algebraically, this is equal to 3 times some number, but this number should be an integer. Okay, so let's say this is 3 times z, okay, where z is an integer. Okay, so that's what this assumption is saying. Okay, so we're done with step 2. Then in step number 3, which is the inductive step, we want to test whether the formula is going to be true for the next bigger integer is true. For the next bigger integer is k plus 1. Okay, so the formula being true for n equals k plus 1 means that if we plug in k plus 1 here, we are going to still get something that's divisible by 3. So let's say here IA, whether P of k plus 1, so P of k plus 1 we're going to get by replacing every k by k plus 1 here. So this is going to become k plus 1, and this is going to become k plus 1 squared, and then plus 2. So I want to test whether this is divisible by 3, so there's a question mark there. So that's provided that this one is true here. Alright, so the thing we're going to do is that we're first going to expand this, okay? So if we expand what is inside the square brackets, we're going to have k squared plus 2k plus 1, and then plus 2, so it's going to be k squared plus 2k plus 3. Then if we multiply out, if we multiply all these terms by k, we're going to have k cubed plus 2k squared plus 3k. Then if we multiply all these terms by 1, we're going to have k squared plus 2k plus 3. Then if we collect like terms, this is going to be k cubed plus 3k squared plus 5k plus 3. So that is our P of k plus 1. Now, so always what we do is we prove or otherwise this using step 2. So from step 2, we are going to remove brackets here. So remove brackets here. So we have k cubed plus 2k is equal to 3z. Remember, z is a positive integer. Then we can actually make k cubed the subject of the formula here is going to be 3z minus 2k. So we can take this and substitute it in here. So then P of k plus 1, which is currently k cubed plus 3k squared plus 5k plus 3. Then instead of k cubed, we are going to substitute this one in here. So we're going to have 3z minus 2k, and then plus 3k squared plus 5k plus 3. Then on removing the brackets, we're going to have 3z. This and this is going to give us 3k. So this 3k squared is this one, and then the k terms will be 3k, and then plus 3. So what we have here is 3 into z plus k squared plus k plus 1. But since z is an integer, k is an integer, y is an integer, so k squared is also an integer. Sum of integers is an integer. So this here is an integer here. So this p of k plus 1, we've just shown that it is equal to 3 times an integer. If it is 3 times an integer, it means it is divisible by 3, which is divisible by 3. So that implies that this proposition is going to be true for all natural numbers. Right, so that covers the first one. Let's now go to the second one. So in B, we have P of n equal to 5 to the power n minus 5. This is always divisible by 4. All right. So for step 1, we're going to let n be equal to 2 again. P of 2 is going to be 5 squared minus 5. This is 25 minus 5. This gives us 20, which is divisible by 4. So the proposition is true. Then we're going to go to step number 2, which is the hypothesis step. We are going to assume that P of k, which is going to be 5 to the power k minus 5, we are going to assume this is divisible by 4, where k is also a natural number. What this assumption is saying is that 5 to the power k minus 5 is going to be 4 times z, where z is an integer. Okay, so that is step number 2. Then in step number 3, we're going to test whether, so we're now doing the next bigger integer, so it's going to be P of k plus 1. So wherever there is k here, we're going to replace it by k plus 1. It's going to be 5 to the power k plus 1 minus 5. So we want to test whether this is divisible by 4. Okay, we do this by using the statement from step 2. Okay, so we're going to say here from step 2. So what we can do is we can make 5 to the power k the subject of the formula there. So 5 to the power k is going to be 4z plus 5, and then we can substitute this into that p of k plus 1. So notice that 5 to the power k plus 1 you can write as 5 to the power k times 5. And then we're going to take this here and substitute it there. So we're going to have 4z plus 5 times 5 minus 5. So this is going to be 20z plus 25 minus 5. This is going to be 20z plus 20. This is 4 into 5z plus 5. Now, since z is an integer, then 5z is also an integer. So this is an integer plus an integer, so this whole thing is an integer. So we've just shown that this is divisible by 4 because it's 4 times an integer. So we're going to say which is divisible by 4 because it's a multiple of 4 really. So hence the proposition is true for all natural numbers. All right, so that's part B. We are now going to go to part C. In part C, we have P of n is equal to 4 to the power n plus 1 plus 5 to the power 2n minus 1. The proposition is that this is always divisible by 21. Okay. So, step number 1, let n be, let's go with n equals 1 this time. So P of 1 is going to be 4 to the power 1 plus 1 plus 5 to the power 2 times 1 plus 1. This is going to be 4 squared. This is going to be 5 to the power 1. It's going to be 16 plus 5. It's going to be 21. So that is divisible by 21. So we say which is divisible by 21. So the proposition is true for this base case. Then in step number 2, we are going to assume that when n is equal to k, then 4 to the power k plus 1 plus 5 to the power 2k minus 1 is divisible by 21. What this is saying is that 4 to the power k plus 1 plus 5 to the power 2k minus 1 is 21 times z, where z is an integer. Okay, so that is step number 2. Then step number 3, we want to test whether P of k plus 1 is also going to be divisible by 21. Now remember, in this step, we'll replace every k by k plus 1. So wherever there is k, we're going to plug in k plus 1. So this is what we're going to have 4 to the power. So where there was k, we put in k plus 1. Okay. And then plus 5 to the power, sorry. I exactly did the wrong thing there. So there we have 2k minus 1. The thing we're going to replace by k plus 1 is this one. Okay. So what we're going to have now is 5 to the power 2. Then in red here, I'm going to write k plus 1. And then the minus 1 is what was there. So I want to test whether this is divisible by 21. Okay, then we're going to simplify these exponents here. So let's do that. So p of k plus 1, remove brackets there, it's going to be k plus 1 plus 1. So that's going to be k plus 2. Okay. And then for this one, if you remove brackets, you're going to have 2k plus 2 minus 1. It's going to be 2k plus 1. So our new exponent here is going to be 2k plus 1. Okay, so this is the thing I want to prove whether it's divisible by 21 or not. And then as usual, we're going to use our statement assumed true from step number 2. So in step number 2, we had 4 to the power k plus 1, 5 to the power 2k minus 1 is equals to 21z. Now, so what we could do here is we could make this one the subject of a formula. So we're going to have 4 to the power k plus 1 is 21z minus 5 to the power 2k minus 1. Then this we will substitute into that p of k plus 1. Maybe let me want to substitute it somewhere there. So let's rewrite p of k plus 1 is 4 to the power k plus 2. 4 to the power k plus 2 is the same as 4 to the power k plus 1 plus 1. It would appear like we're going in circles, but we aren't exactly going in circles. Then that first term, when I can now write as 4 to the power k plus 1 times 4 to the power 1 plus 5 to the power 2k plus 1. Yeah, it's plus 1 here because I am rewriting this one there. Alright, and then this now is the same as this. So we can take that and plug it in there. When we do that, we are going to have 21z minus 5 to the power 2k minus 1 all times 4, and then plus 5 to the power 2k plus 1. 21 times 4 is going to be 84. Z, this one is going to be 4 times 5 to the power 2k minus 1. Plus 5 to the power 2k plus 1. So just in case you're wondering, notice that these two, we can't multiply them because the bases are different and the powers are different. This is power 1 here and this is power 2k minus 1 there. So we can't multiply them. However, what we're going to do, we're going to 84z. If we write this as 4 times 5 to the power 2k, then 5 to the power negative 1. And write this one as 5 to the power 2k, 5 to the power 1. Then all of a sudden you will notice that we have a like term or a common factor there. So that factor we are going to factorize, of course. So let's do that. So this is going to be 84z. I'm going to start with the plus case, this term here. So 5 to the power 2k, open brackets. From this, we're going to have 5. Then minus from this term, we're going to have 4 over 5. 5 to the power negative 1 is 1 over 5. So this is going to be 84z plus 5 to the power 2k. If we write this as one fraction, that's going to be 25 minus 4. So this is going to be 21 over 5. Then if we like, we can write this as 5 to the power 2k minus 1. That's going to be coming from this one here, the minus 1. Then times 21. And then now both terms have got 21 as a common factor. So this is going to be 4z. 5 to the power 2k minus 1. Now, z is an integer. So 4z is also an integer. K is an integer, so 2k minus 1 is an integer. 5 to the power, that is an integer, is also going to be in an integer. Integer plus integer is integer. So this is 21 times an integer. So this is divisible by 21. So this is telling us that the proposition is going to be true for all counting numbers. So that completes that proof. All right, so that was example number C. We're going to stop the video at this point, and then we'll do example number D in the next video, and also give you some 2 exercises to try for yourself. Actually, maybe it's going to be 3 exercises. Okay, so in the next video.